Okay, so we're going to go over some of the basics of motion, some of those vocabulary, speed calculations, and stuff like that that you need to know for our unit test coming up. So first, compare and contrast Alan's path and Ava's path using the words distance and displacement. Okay, so let's look at these paths here. Okay, Ava went straight from the west gate to the east gate. Alan also went from the west gate to the east gate, but he took this curvy, loopy path. Okay, so what we can say is that if you just compare the beginning and the end, they had the same displacement. It's 100 meters, okay? So Alan and Ava had the same displacement, which was 100 meters. However, Alan covered more distance because he did not take a direct path. Okay, so they have the same displacement but different distances. Okay, Alan he went this way a little bit and this way a little bit, and then he went backwards and then around and then backwards, and then he went toward it, but then he went backwards, and okay, his direction changed a lot. Overall, he ended up with the same change in position, but he covered a lot more distance, which isn't concerned with just the overall change in displacement, but the path you took there. Okay. All right, and then I'm going to go over a couple examples. First, a conversion one. A cheetah can move at a speed of 120.7 kilometers per hour. What is its speed in miles per hour? And we're given this conversion factor right here. So all I have to do is convert the kilometers to miles. So I know that 1 mile is 1.609 kilometers. Kilometers and kilometers cancel out. I'm left with miles over hours, or miles per hour. And I plug that into my calculator, 120.7 divided by 1.609, and I get 75.02 miles per hour. Keeping it at 4 sig figs since this number had 4 sig figs. Yep. Let's do a speed problem. Yep. A blue whale migrates 4,200 kilometers in approximately 2,900 hours. What is its average speed during this 4-month trip? So we use the equation velocity equals distance over time. The distance is 4,200 kilometers. The time is 2,900 hours. We divide that and we get 1.448 something. We'll round it to 2 sig figs since these numbers each had 2 sig figs. So 1.4 kilometers per hour. All right, let's do one more. A baby crawls at a speed of 3 miles per hour. How far could it crawl in 0.75 hours? Okay, so this time we're looking for distance. So if velocity equals distance over time, okay, if we're solving just for distance, distance equals velocity times time, which you might remember from our position versus time graphs that we've drawn and various stuff in the class. Also, it's how the units work out. So distance equals velocity, 3. Just so that it's clear what I'm doing, I'm going to rewrite mph as miles per hour. That should make it a little bit more clear for you guys. So miles per hour, okay, times 0.75 hours, Hour and hour cancel off. Sorry about that. And you get 3 times 0.75, which is 2.25 miles. Okay. I'm not going to completely go over 8 and 9, but I did just want to recognize. So if a teacher walks the path above, she goes 4, 6, 7, 8, 9, 6 plus 6, 12 meters. Okay, so it's 12 meters is what the perimeter is. So you can find that to use its speed. If you were doing velocity, however, velocity is displacement over time. So if you go this and you end up back where you started, there is no displacement. There is no change in position. So her average velocity, because she went positive and then negative, they're going to cancel each other out. There's no displacement. It's going to be 0 meters per second. Okay. So let's go ahead and look at some of the graphing over on the back now that we've done those. I'm just going to pick some random graphs to explain. On this one, I'll do graph A and B. So A, it's starting out at a high position and going towards 0 position. So that would be constant speed because it's straight. So that's constant speed toward the origin. That's graph A. If we look at graph B, at first, every second, the position is changing a lot. But if you look at like a second over here, the position barely changes. Okay, so this graph is slowing down as it moves away from the origin. So graph B is slowing down for those position versus time graphs. Velocity versus time graphs are a little different. Okay, if we look at A, it stays at the same speed the whole time. Okay, so that is constant speed. Okay, now one of these is speeding up the whole time or speed increasing the whole time, and the other one is getting up to speed and then staying at a constant speed. I'm sure you guys can figure out which is which out of those two. These graphs, you're going to make up your own story, but I did just kind of want to show you what's going on. So on the position, it starts out covering a lot of position, then it stays at the same spot. So the speed decreases, and then the speed is 0. Everywhere that the graph is flat here, the speed isn't changing. That's a point here where the speed is 0. So there's 1, 2, 3, and then that one, 4 points where it's 0. 1, 2, 3, 4 points where it's 0. The part that it's the fastest is where the slope is the greatest, which looks like it's right here on the end, which you can see there as well. The reason that it's a slanted line here is because it's a curved line here. This one is gradually slowing down, so this one is slowing down. Okay, so if we look at it, he slows down, then he stops, he walks over somewhere else, and then he stops, and then he walks back, and then he stops, and then he walks over again, and then he stops, and then he goes away, runs back to where he started. Okay, since this is speed versus time, the direction doesn't matter. It's all going to be positive. If it were velocity versus time, we would see some graphs down here at the bottom. But it's speed versus time, so we don't. So make up a story about that. Hopefully that was helpful.